Every modern weapon depends on a whisper from space, a drone over a battlefield, a cruise missile hugging the terrain, a cargo ship threading a narrow channel, your phone finding the fastest way home. They're all listening for the same thing. A radio signal from satellites roughly 20,200 kilometers above Earth, and by the time that signal arrives, it barely exists. A GPS satellite transmits about 25 to 50 watts of power, roughly the same as a household light bulb. But instead of lighting a room, that energy is spread across an entire planet. By the time it reaches your receiver, the signal strength is approximately minus 160 decibels relative to a watt. That's less than a quadrillionth of a watt. To put that in perspective, the GPS signal hitting your phone right now is weaker than the background thermal noise generated by the phone's own electronics. Your receiver isn't just listening, it is pulling data out of pure static. And that is the ultimate vulnerability, because if the real signal is already buried below the noise floor, it doesn't take much to drown it out. Or worse, replace it. To understand the attack, you have to understand the math. GPS doesn't actually measure distance, it measures time. Each satellite carries an atomic clock. Every few milliseconds, it broadcasts a timestamp encoded into a digital pattern called a pseudo-random noise code, or PRN. These codes look like random static, but they are mathematically precise. Each satellite has its own unique sequence. Your receiver generates an identical copy of that sequence internally and slides it back and forth in time until it finds a perfect match with the incoming signal. This is code phase acquisition. When the patterns line up, the receiver detects a correlation peak. That peak reveals exactly how long the signal took to travel from space to your hand. Multiply that time by the speed of light, and you get your distance from that satellite. Do that with 4 satellites, and the math converges. You now have your latitude, longitude, altitude, and, most importantly, atomic level time. But here's the catch. Because the signal is so weak, the receiver can't see it instantly. It has to integrate the signal over time, averaging out the noise until that correlation peak emerges. It's like listening for a faint rhythm in a crowded stadium. Once the receiver locks onto that rhythm, it will follow any signal that provides a stronger, clearer version of that same pattern. That's where the hijack begins. Jamming is the brute force of electronic warfare. You don't try to be clever, you just get loud. The real signal is incredibly weak, which gives a ground-based transmitter a massive advantage. Signal strength follows the inverse square law. It falls off with the square of the distance. The satellite is 20 million meters away. A jammer might be 200 meters away. That makes the jammer 100,000 times closer. Even with a tiny battery, the local jammer wins. A 1-watt jammer, smaller than a TV remote, can deny GPS for several hundred meters. A 10-watt jammer can blind an aircraft miles away. We've seen cigarette lighter jammers used by truck drivers to hide from their bosses accidentally shut down entire airport navigation systems. Most jammers just pump out white noise centered on the L1 frequency, 1575.42 MHz. To your receiver, the noise floor simply rises until the correlation peaks vanish. For a smartphone, it's a no-signal icon. For a precision-guided glide bomb, it's a catastrophe. Without GPS to correct its course, a drone's internal sensors will drift. A weapon designed to strike within a few meters might suddenly miss by hundreds. But jamming is noisy. It's an alarm bell that tells everyone they're under attack. Spoofing is different. Spoofing is a ghost. Spoofing doesn't remove the signal. It lies to it. To spoof a GPS, an attacker transmits a fake signal that is perfectly structured. It uses the same PRN codes, the same frequency, and the same timing. But the attacker sends it just slightly stronger than the real one. The receiver, designed to lock onto the strongest valid match, latches onto the fake signal. At first, the spoofer matches the true position exactly. The receiver sees nothing wrong. Then the attacker slowly shifts the timing of the fake signal. This is carry-off spoofing. A tiny timing shift becomes a tiny distance error. The receiver follows the drift, believing it is moving when in reality it is sitting still, or vice versa. It is the perfect crime. The signals are clean. The math works. The navigation solution converges. The pilot or the drone operator sees a perfect green status on their screen, while they are being led miles off course. Why is this so easy? Because civilian GPS, the L1CA signal, was designed to be open. It is unencrypted, unauthenticated, and its source code is public knowledge. Military receivers use encrypted signals like M-code, which require a cryptographic key. But the vast majority of our world, civilian drones, ships, and cell towers, runs on the open L1 signal. Today, you don't need a government lab to do this. You need a software-defined radio, a laptop, and a cheap amplifier. In 2018, researchers at Virginia Tech built a working GPS spoofer from off-the-shelf hardware for about $225. That was enough to generate a fake constellation of satellites and silently redirect a car's navigation to the wrong destination. We are already seeing the consequences. In the Black Sea, ships have reported their GPS coordinates, showing them at inland airports. In conflict zones, aircraft have received false pull-up warnings because spoofed data told their terrain avoidance systems they were flying into a mountain that didn't exist. Modern warfare assumes GPS is a given. Drone swarms use it to maintain tight flight geometry. Artillery shells use it to adjust their fins mid-flight. Even troop movements rely on digital maps synced to GPS timing. If you remove GPS, precision disappears. If you spoof GPS, precision becomes a liability. A swarm can be redirected into a building. A navigation system can guide an army into an ambush. And because spoofing looks legitimate, the operator might not realize the map has shifted under their feet until it's too late. So, how do we fight back? The first line of defense is inertial navigation. INS uses gyroscopes and accelerometers to track movement from a known starting point. It doesn't need satellites, so it can't be jammed or spoofed. But INS is not perfect. Even high-end systems drift. Without a GPS fix to reset the clock, those errors grow every second. Militaries are now moving toward what's called navigation warfare. Building systems that don't need the whisper from space at all. Controlled reception pattern. Antennas can detect signals coming from the ground and filter them out, only listening to the sky. Vision-based navigation lets drones look at the terrain below and match it against satellite imagery to find their way. And magnetic mapping allows platforms to navigate using the Earth's unique magnetic fingerprints. The goal is a world where GPS is optional, not essential. GPS feels permanent. It's become a fundamental utility like electricity or water, but it's built on a foundation of signals weaker than the static on an old TV. A $225 transmitter can silence the satellites. A smarter one can rewrite them entirely. We imagine future wars will be won by the biggest engines or the fastest missiles. But the real battlefield might be much quieter. It's the math inside a receiver. It's the difference between two identical correlation peaks. Because in a world dependent on the map, the side that controls the signal controls reality. This is Null Inertia, the point where technology meets territory. Thanks for watching.